Okay, so last time we started with three-phase circuits, and we discussed that in a three-phase circuit we have actually three different voltage sources connected in such a manner that the voltage magnitudes of these three sources are equal, and the phase difference between them is 120 degrees apart. Fine. So electrically they are 120 degrees apart from each other. Uh, there is we are not talking about mechanical angle here. There is no such role as such in of a mechanical angle in this particular case, but definitely when you will be talking about three-phase electrical machines, they are both the mechanical angle as well as the electrical angle play an important role. We will learn about that there only. So in a three-phase circuit, you have three different voltage sources uh, of same magnitude but 120 degree phase apart from each other. We then discussed how we can connect the three voltage sources either in a star fashion or in a delta fashion, and what will be the voltage across uh, what will be the voltage across different phases, what will be the voltage between phases, and what will be the voltage between a phase and a neutral point, what is phase voltage, what is line voltage, all of that. We have to discuss four different types of connections, and once we do these four different connections, we study these, will be actually that will complete our course. So these four different connections are star star, star delta, delta delta, and delta star. So first of all, we are starting with the star star connection. So we have a three-phase voltage source. This three-phase voltage source is actually connected in a star fashion. So we have VA, we have VB, and VC. In a star, as I told you, there is also a neutral point, and at the point of common coupling, this is where all the three voltage sources will meet. This is known as the neutral point. So this is your source side. Similarly, on the load side, you will be having a load connected in a star fashion as well. There's a neutral point here as well, so we can directly connect the two neutral points. Fine. Let the current that is flowing in this particular line, let this current be IA, let this current be IB, let this current be IC. So this is your star connected three-phase element where we have a three-phase voltage source connected to three loads. The three loads here are represented by ZA, ZB, and ZC. What we'll be actually assuming is that ZA, ZB, and ZC are equal in magnitude. We're considering a balanced connection. In a balanced connection, balanced connection means that the magnitude of voltage are same. VA is equal to VB is equal to VC. Now let VA be equal to VP angle 0 degrees. If VA is equal to VP angle 0 degrees, that means VB will be equal to VP angle minus 120 degrees, and VC will be equal to VP angle minus 240 degrees, or you can even say that minus 240 means simply plus 120 degrees. So these are your three phase voltages. The voltage between a line and a neutral. Line means simply here this voltage between this line and this neutral connection is VA. This is known as the phase voltage. And we also already derived this in the last lecture, that VAB, you will be having you will be having 6 different line voltage. VB is this voltage. VAB is this voltage, sorry. It is the voltage between a line and a line, or you can say between a phase and a phase. That is known as the line voltage. So VAB, we calculated this. This will be equal to root 3 VP times angle 30 degrees. And VBC will be root 3 VP angle minus 90 degrees. And VCA will be root 3 VP angle minus 90 minus 120 that is minus 210 degrees. This will be VAB. VBA can therefore simply be minus VAB, that is root 3 VP 30 minus 180 that is minus 150 degrees. VCB will be root 3 VP angle minus 90 minus 180, that is minus 270, or you can simply say plus 30 degrees. And VCA or VAC will be root minus VCA, that is root 3 VP angle minus 210 minus 210 means 30 degrees. So 30 minus 180 means minus 210 minus 1 plus 150 degrees. 150 means this will be minus 30 degrees. Fine. So these are the phase voltage, and these 6 represent the line voltage in this particular case. Now since we have a load connected in this system, therefore IA, IB, IC will also be flowing in this particular case. Now what will be the value of IA, IB and IC, that we have to calculate. So we can write IA is equal to, now for a star connection we know that the phase current and the line current will be same. There is no difference between phase current and the line current here. Whatever amount of current is actually being generated at this voltage source, same amount of current is flowing into this line. So IA, they are both same in this case. So phase current, line current will be same. So we have to actually find out only these three current values, IA, IB and IC. So what will be IA? IA will simply be equal to the voltage across this particular impedance, that is ZA. The voltage across this particular impedance ZA, if you can see, it is simply equal to VA divided by ZA. Fine. So IA will be equal to VA divided by ZA. IB will be equal to VB divided by ZB, and similarly IC will be equal to VB divided by ZC. Now these are the three volt. These are the three currents. These are the three, you can say, phase currents or line currents in this particular case, as they are same for a star connection. For this particular connection, that is star-star connection. IA, IB, and IC, that is the current flowing through these three particular impedances, ZA, ZB, and ZC, will simply be equal to VA divided by ZA, VB divided by ZB, and VC divided by ZC. Now, if we know actually what are these loads, say for example, we have simply three resistive loads connected like RA, RB, and RC, we can simply say that IA will be this much, IB will be this much, and IC will be this much. One more thing to note here is that there will be some amount of current that will be flowing into in this particular neutral branch. Now, what will be that current that will be flowing in this branch? That will simply be that can be represented by IN equal to IA plus IB plus IC. Now, since we have assumed that our system is balanced, the magnitudes of VA, VB, and VC they are same, and we are also assuming that ZA, ZB, and ZC they are same. So whatever amount of current is going into this particular branch, that will be equal to IN. And algebraically, you'll find out that this current will be equal to 0. This has to this condition has to be met. That is, the neutral current has to be equal to 0 for a particularly balanced system. IN is actually equal to minus of this thing. Right? IN is in this direction, IA is in this direction, IB is in this direction, IC is in this direction. IN is also into this direction, so IA plus IB plus IC plus IN is equal to 0. Or in other words, we can say IN is equal to minus IA plus minus IB minus IC. Fine. So this particular current for a perfectly balanced system has to be equal to 0 because of the phase difference between the voltage and the magnitude of the voltage. This will come out to be equal to 0. So we'll actually also see this when we do some numerical on this. We'll actually find out that this current will come out to be equal to 0. So we can take one particular example from which we can actually find out the values of these currents extra and uh, see how actually we can analyze a star-star circuit. So we have one voltage source here. It is equal to 110 angle 0 degree volts. This is 110 angle minus 120. This is 110 angle plus 120 degree volts. This here is connected to 10 plus 8J. So you have this particular circuit 10 plus 8J, 10 plus 8J ohms. So you have perfectly balanced voltage source, three-phase voltage source connected to a perfectly balanced three-phase load. You have to find out for this particular case, you have been asked to find out IA plus IB. You have to find out IA, IB, and IC. Okay? And we'll be actually finding out whether or not IN will be equal to 0 or not. So as we saw for this particular case, IA is simply the voltage across 10 plus 8J, that is VA divided by ZA. In this particular case, it is 100, 110 angle 0 divided by 10 plus 8J. So this is equal to 6.81 angle minus 21.8 degree amperes. Fine. IB will similarly be equal to VB divided by ZB. VB here is this voltage 110 angle minus 120 divided by ZB, that is 10 plus 8J. This will come out to be equal to 6.81 angle minus 141.8 8 degree amperes. IC will be equal to VC divided by ZC, that is 110 angle plus 120 degrees divided by 10 plus 8J. So this will come out to be 6.81 angle uh, minus 261.8 degree amperes. You can write minus 261.8 degree amperes. Fine. तो सिंपली जो तीन इम्पीडेंसेस है आपके उसके अक्रॉस जो भी वोल्टेज है डिवाइडेड बाय दैट इम्पीडेंस you will find out the three line currents IA, IB and IC. So these are your three line currents. Now you can also verify whether IN, that is IA plus IB plus IC, whether this is equal to 0 or not. Fine. You can actually find this out. Your minus low or plus low, in either case this has to be equal to 0 and you can actually calculate that. You can simply sum these three up and you'll find out that the neutral current will be equal to 0. Now this is a perfectly balanced system where your three-phase load as well as three-phase source were having the equal magnitudes. ठीक है, जहाँ पे आपका equal magnitudes नहीं होगा, जहाँ पे आपका voltage and the load is actually imbalanced or the voltage is imbalanced, you will not be actually getting IN equal to 0 in that case. Okay, let's first continue. We'll do the second type of connection, that is star delta connection. We'll do numericals later on. Star delta connection. So a star delta connection means we have a system where our source, three-phase source, is connected in a star fashion, while as our load, it is connected in a delta fashion. So we have VA, VB, VC, the three-phase voltage. You have Z. Since we are assuming that the load is balanced, so we can say simply ZL, ZL, and ZL. Fine. Let us just mark these points A, B, C. ठीक है. अब यहाँ से कुछ करंट फ्लो हो रही है, दैट इज IA. IA is the current flowing in this path. IB is the current flowing in this path. IC is the current flowing in this path. These are your phase voltage in this particular case. That's actually generated from the system. But अब यहाँ पे क्या हो रहा है, यहाँ से कुछ करंट है. Let's say this is IAB. Let us assume the current in this path is IBC, and the current in this particular path is IC. So you have a star connected voltage source, but you have a delta connected load source. The delta will not be having any point of common coupling, so there is no neutral point. So ये जो आपका flow neutral point होगा इस case में, it is actually grounded. Simply in practical circuits, what we do is we simply ground the neutral point because there's nothing on the load side, no point of common coupling where you can actually connect this thing. Now let us again assume that VA is equal to VP angle 0 degree volts, VB is equal to VP angle minus 120 degree volts, VC is equal to VP angle minus 240, or you can say plus 120 degree volts. These are the three phase voltages that are originating from the source. And now what will be the voltage across the lines? So the voltage across this will be VAB. Okay? So VAB, as we know, is equal to root 3 VP angle 30 degree volts. What will be the voltage that will be across B and C? Okay? Voltage across this point VBC. That's also actually the voltage across this particular point. That is, let me keep these. Let me name these source volt loads. Let them be ZAB, ZBC, ZCA. Okay? So VBC is the line voltage. It is also the voltage that is impressed across the load ZBC. Similarly, VCA is the voltage that will be across, it's a line voltage and it will be impressed across this particular इसके across जो voltage होगी that will be VCA. So VAB is root 3 VP angle 30 degrees, VBC is root 3 VP angle minus 90 degree volts, and VCA is root 3 VP angle minus 210 degree volts. Fine. Minus 210 लिखो या plus 150 लिखो. That's one and the same thing. Now what is IA, IB and IC? To find out IA, IB and IC, first of all we need to find out IAB, IBC and ICA. Now IAB is the current that is flowing across the impedance ZAB. So you can from the keeping the direction of current into mind, IAB is simply equal to VAB divided by ZAB. That is the impedance across this particular point. IBC is VBC divided by ZBC. ICA is VCA divided by ZCA. So these will be the three phase currents. These are the currents that are flowing in the load circuitry. These are the three phase currents in this particular case. That's across individual loads. What will be the current? That is IAB, IB and ICA. So these are the phase currents here. Now, since we know IAB, ICA, and IBC, we can find out the line currents, and the line currents are IA, IB, and IC. IA will be equal to what? It is simply equal to IAB minus ICA. IB will be equal to what? It will be simply equal to that is the current in this particular branch by applying KCL at this particular node. At node B, IB is equal to IBC minus IAB. Fine. And at node C, by applying KCL, IC will be equal to IC plus IBC is equal to ICA, or you can say IC is equal to ICA minus IBC. So once you will be knowing actually ZAB, ZBC, and ZCA, you can find out the phase currents. That's IAB, IBC, and ICA. That's actually the current flowing into a particular load. But this is not actually the current that's actually flowing in the transmission lines. That is actually the line that will be carrying current to this load, that will be carrying different amount of current. And what will those current values be? That will be IA, IB, and IC. So to find out IA, IB, and IC, you can simply apply KCL at these three different nodes A, B, and C. You can find out the three line currents, IA, IB, and IC. Uh, Let's do one numerical on this. You have a balanced star connected source, 100 angle 10-degree volts. If this is 100 angle 10-degree volts, this will be 100 angle 10 minus 120. That is minus 10, 110 degrees. And this is minus plus 100 angle. If that is 10 degrees, this is 10 plus 120. That is 150 degree volts. Now this star connected circuit is connected to a load having impedance of 8 plus 4j per phase. That means in each phase you have 8 plus 4j connected. So you have been asked to find out the phase currents as well as the line currents in this particular case. So line current here refers to IAB, IBC, and ICA. These are the phase currents, and the line currents are IA, IB, and IC. You have to calculate these different values. So IAB is equal to what? It is equal to VAB divided by ZAB, where uh, VAB is the line voltage and not the phase voltage. So it is the voltage across this and this. That's it. In other words, you can simply say it is 100 angle 10 degrees minus 100 angle minus 110 degrees. You can either use this, or you can simply calculate it by subtracting VA minus VB, or you now know generally what is the case. VAB is root 3 times Vp, that is 100, and it is at an angle of 30 degrees when this particular angle is 0 degrees. So in this particular case it will be 40 degrees. So this is 173 angle 40 degrees. And 73.2 angle 40 degrees. And ZIB, it is 8 plus 4J. So IAB is coming out to be what? 19.36 angle 13.43 degree amperes. So this is the value of IAB, that is the phase current. In the particular phase, what is the amount of current? Now, since we know that this is a balanced circuit, all the voltages are same, all the loads are same. IBC will be also having a magnitude of 19.36. If this is 13.43 degrees, this will be 13.43 minus 120, that is roughly 106.57 degree amperes. ICA will be equal to 19.36 angle 13.43 plus 120 degrees, that is 133.43 degree amperes. So these are the values of three phase currents. Now we need to find out IA. IA is simply equal to IAB minus IBC. IA is equal to IAB. At this particular node, at node A, applying the KCL, IA plus ICA is equal to IAB, or you can say in other words, IAB minus ICA is equal to IA. IAB is 19.36 angle 13.43 degrees minus 19.36 angle ICA is 133.43 degrees, 19.36. This will come out to be equal to 33.53 angle minus 16.57 degrees. So this will be the value of IA. IB will similarly be equal to 33.53 angle minus 16 minus 120, that is minus 136.57 degrees, and IC will be equal to 33.53 minus 16 plus 120 degrees, that is roughly 103 degrees. So, so these are the three values, 103.43 degrees. These are all in amperes. We have found out the phase currents as well as the line currents in this particular case. You have to find out, since your source is connected in a star fashion, so that means phase voltage and line voltage cannot be same. And since your load is connected in a delta fashion, that means your phase current and line current will not also be same in this particular case. With a star star, the case was that because phase voltage and line voltage were not same, but phase currents and line currents were same. In a star star connection, what happens is load voltage is root 3 times the phase voltage. The line current is equal to phase current. So far in a star delta we have seen that line voltage is equal to root 3 times Vp, and line current is also equal to root 3 times the phase current. Uh, your line voltage, your line currents, in this case, they are root 3 times the phase currents. That means जो आपके line phase current का जो magnitude था, in this particular case that was 19.36. You can find out the phase currents IA, IB. You can find out the line currents IA, IB, and IC will be having a magnitude of root 3 times that of 19.36. That is 33.53. So this is we have to actually find this. We have to complete this table. So far, what we have seen in a star star and a star delta is that line voltage in a star star is equal to root 3 times Vp, but line current and phase current are same. But in a star delta, the line voltage is also root 3 times Vp and line current is also root 3 times Ip. So now this is actually once we actually complete this complete table, we'll see where we can mm, where we can opt for star star connection, where we can opt for star delta connection, where we can opt for delta delta or a delta star connection. Now depending upon the value of these voltage and currents. Fine. So in a particular case, you might be needing more voltage but lesser current, so you can opt for star star. But in some other case, you might be needing more voltage as well as more current, so you'll opt for star delta. Delta star we have to study, but once we study that, we can assume we can say that for what amount of current, for what amount of voltage, what sort of connection is better utilized. All these cases are only for balanced circuits. You can also, now since you know how the procedure goes, even if you have been given an unbalanced circuit, you can find out the value of voltage and currents across both line voltage as well as phase voltage as well as line currents and phase currents. For a balanced circuit, it is simple that you have to simply find out one particular line current. Rest of the line currents you can now directly say from that particular line current they'll be having the same magnitude and they'll be shifted by 120 degrees from each other, and the same goes with phase currents or phase voltage and line voltage. You have to find out only one value, rest of the values are automatically available to us, but only for balanced circuits, not for imbalanced circuits. ठीक है, तो दो connections हो गए आज. We'll continue with this tomorrow, and we'll do the delta delta and the delta star connection tomorrow, and we'll find out how they are different from these two. After that, we have to actually also find out the power equations in these four different circuits or three-phase circuits in general. That will be all for today.